Hi, my name is Simon Barrera. I am a student of chemical engineering, and here I want to talk about enzymatic replacement therapies for inborn diseases. At first, I would like to introduce with what a protein is. As you know, a protein is a chain of amino acids attached together that when they are folded over themselves, you will get any kind of protein. The function of the protein depends of the geometry and some other factors, but this is one of the most important. Here I want to talk specifically about sulfatase human enzymes. So, when people they are not able to produce their own protein, and specifically the sulfatases ones, they got in some of these diseases. As you can see, this is the most popular one. It is called mucopolysaccharidosis or the Hunter syndrome. There is also metachromatic leukodystrophy, ichthyosis linked to the chromosome X, and many others. So what I wanted to do is to help these people, because actually the problem is that there are solutions actually nowadays for these people, but they are too much expensive and people cannot afford that. So what I propose is to get more solutions for this disease. And what I thought is to use E. coli bacteria. So this is the thing. There are proteins which can activate other proteins. So here I propose two enzymes that can activate my sulfatase protein. The thing here is that people can produce the sulfatase proteins, but not in its active form. I mean, they can produce the sulfatase, but it is not going to work unless it is in its active form. So everything starts here in the Golgi complex within your cells. So here the sulfatase is produced, and what happens then is that there are two proteins that may activate our sulfatase. The activation mainly consists in a modification in the active site of the cysteine to 4-methyl. After this change, we can get our enzyme activated or maturated. Also, I need to say that this one is already been demonstrated. So this one is it still needs to be demonstrated. Well, here I came with some computations. I extracted or I computed a YDEM structure, and I compared it to one that already exists. The similarity is very high. As you can see, we got this value, which is 0.15 angstroms. This is a very small, tiny difference between these two proteins. After this, I came with some other computations that are about fitting our computed protein into the other one, into the sulfatase, to study their relationship. As you can see, I here computed some energies, and the most negative it is better. And as you can see, our protein falls over this yellow part that it is the active site. All these yellow parts are active sites, and the thing is that I have to get this yellow part with this yellow part. So as I said, I got negative energies, and in theory, here I say, well, this YDEM enzyme works with to activate my sulfatase proteins. In my computer works. Then what I wanted is to try it in the laboratory, but well, I started here. I insert the gene for my carry protein here, and what I did is that I at the end insert this that is called a plasmid, bacteria plasmid. I insert it into E. coli and made it to produce my protein. It is YDEM what I wanted it to produce. Here I have some results. I knew these dishes have my bacteria with the protein, but I couldn't finish it. So as a future work, it is still needed to demonstrate that it works in the laboratory and compute some cost of the solutions. Here I say that I facilitate the work in the way that the E. coli is the one of the world's most researched bacteria, and it can be found everywhere. So it is, I would say, it is more affordable for people to get to this solution. Also, as I say, people could improve methods, reduce costs to commercialize the solution at acceptable prices. This technique can be still extrapolated to other inborn diseases to facilitate people's life. Thank you.